We're going to now discuss the Doppler effect. Now, the Doppler effect is something that you have come across before, no doubt. If you haven't come across its physical background, you'll certainly have experienced it in the real world. We're going to specifically talk about the non-relativistic example of the Doppler effect. In this case, it arises from relative movement between the source and the observer, resulting in changes of the observed frequency. So as a sound source is moving, it can catch up with the sound waves it is emitting. If we find the source and the receiver are moving towards each other, then the frequency the observer experiences will be different and higher to the frequency that the source perceives. If the source and the receiver are moving away from each other, then the observer would experience a lower frequency. This change in the frequency depends on the relative velocity of the source and the receiver. So if we think of a source moving at the speed u of the source is moving relative to the medium, the wave fronts will bunch in the direction of travel. But the speed of the waves in the medium is utterly independent of the movement of the source. Remember we said about strings that the speed of a wave in a string was dependent on the material of the string, and anywhere on that string the wave would be moving at the same speed. The same principle applies here for longitudinal waves, where the speed of the wave v is entirely dependent on the medium itself and not on the source. Okay, let's get straight into an example. A source at rest emits sound at a frequency of 4 Hz in a medium with speed of sound v equal to 100 meters per second. Calculate how many wavefronts are emitted in 1 second and determine how far the first wavefront travels in that time. From that, determine what the wavelength of the sound waves is. Pause the video and we'll come back to it presently. Okay, so addressing the first part, after a single second, the number of wavefronts emitted by the source is the frequency times the time difference, which gives us 4 wavefronts. Okay, so now we need to find out how far that first wavefront travels in that time. So it's v delta t in this case. So it's speed times time gives us 100 meters. So the first wavefront travels 100 meters in that time. As we've had 4 wavefronts in that time, but the first wavefront has traveled 100 meters. So if we look on this diagram, we could say that this is our 4th wavefront here. That means we've got 100 meters between this point and the source, and 4 wavefronts in between, which means that we have 100 over 4, which gives us a wavelength of 25 meters. Okay, a fairly straightforward example. Let's now take that into an example where the source is moving. Now the source is moving to the right at the speed of the source being 50 meters per second. It's emitting sound at the same frequency of 4 Hz in a medium with the same speed of sound, 100 meters per second. Okay, first question is, how far ahead of the source is the first wave after 1 second? What is the wavelength of waves ahead of the source? And what frequency would a listener in the path of the source receive? Pause the video and we'll come back to it once you've got answers. Okay, so there are a number of ways of solving this problem, but if we remember the previous example, we said that after being emitted, that first wave had travelled 100 meters. Okay, but how far has the source moved in that time? The source in this instance will have moved the time times its speed, 50 meters per second, so it will have moved 50 meters. So we would expect the first wave to only be 50 meters ahead of the source after 1 second. We can also calculate it by finding the difference between the two speeds. So the difference in the speeds multiplied by delta t gives us the same answer. We know that there are 4 wavelengths in that space still, so in 1 second 4 wavefronts have been emitted. There's still 4 in that 50 meter space. So what that means is the wavelength ahead of the source is 50 over 4, which is 12.5 meters. If we want to calculate now what frequency a listener would determine, remember that v equals f lambda, so the speed is the wavelength times frequency. We rearrange that. We find the frequency is the speed divided by the wavelength, which gives us a frequency of 8 Hz. So the observer sees a frequency which is double that which is emitted. And this is an example of the Doppler effect, that frequency shift as there's movement between the source and the observer. In the general case, we can start to think about how to calculate the frequency at any point along the direction of motion. In this case, we can see that the observed frequency, so we're using the prime notation to denote the observed frequency compared to f0, which is the emitted frequency. We can calculate the frequency by just looking at the ratio of the speeds of the receiver and of the source. R is the receiver. We need to pay attention to the signs. The way we do this is that we define the arrow from the receiver to the source being the positive direction. So in this case, if the receiver stands in front of the source, then the positive direction will be towards the left. So in this case, US will then be negative. If the observer stands behind the source, then US will be positive, taking the source away from the receiver. The reason for this is that it allows these equations to work. But we can always check it. We should know that the frequency increases if the source and receiver are moving towards each other and vice versa. So we should expect to see, let's say we're standing in front, we have a negative US. This means V minus US will be smaller than V, and if the observer is standing at rest, this will be V on the top, which means we should end up with a greater observed frequency, and that's in line with our expectations. So let's do another example to test our understanding of the Doppler effect. You're at an outdoor concert where wind is blowing 10 meters per second from the performers towards you. Is the sound you hear Doppler shifted, and if so, is it shifted to higher or lower frequencies? Pause the video and we'll come back once you've thought through your answer. Okay, so the thing to think about here is when you think of Doppler shift, we're looking at the relative speed of the source and the observer. That was the only thing we said that would affect the frequency. That being the case, there would be no relative velocity between the source and observer, so we wouldn't expect to see any Doppler shift whatsoever. So we could say that the source and the receiver are in the same reference frame. So because the air is moving, it's carrying the sound waves at a different speed. So while the speed of the waves and the wavelength might be changed, the frequency itself is not. So we still experience the same frequency coming to us, so we wouldn't observe a Doppler shift. In summary, with the Doppler effect, we have an increase in frequency when source and receiver move towards each other, and we would expect to see a decrease in frequency when they're moving apart. We need to pay attention to the direction of these quantities, and we say that the arrow from the receiver to the source gives that positive direction. Again, pay attention to what the signs are telling you, as that will help you to use these equations effectively. And always pause to think what the results mean. Does the result make sense? And the final thing to remember is that the wave speed is independent of source and receiver speeds. So the wave speed is only dependent on the medium through which the wave propagates.